Using this technology to replace solar cells, what we'll do is set up a system that will work day and night based on the temperature differences between the dry bulb and the wet bulb. This computer simulation allows me to go through and calculate how much energy I'll get out for the amount of temperature of the day and that sort of thing. It allows me to pick what freon or refrigerant or working fluid I want to use, and in this case I want to use CO2 because CO2 has some really cool properties in that it will has a real high pressure rise due to temperature change, and also what it does is allow us to sequester CO2 so that every house in the world can have a certain amount of CO2 to take it out of the environment. What I can do on the working cylinder in this simulation program is I can set the cylinder diameter and stroke so that I can adjust it to configure it for whatever prototype that I'm using. In this prototype, I use a hydraulic cylinder because it can take the pressures, but the reality is we'll really want to build a hermetic system for this sort of thing. The valving system has bidirectional valves which allow gas to be put into the high pressure side of the cylinder while the low pressure side is being released, and vice versa as it switches directions. What I use in this simulation is a shell and tube heat exchanger, but I'm not sure we'll even need it because due to rapid expansion of a natural gas, it'll cool automatically. Also, if we use a series of orifices, as that gas goes through those orifices, increases velocity due to Bernoulli's equation, it will drop in temperature on its own. But for low-hanging fruit, just to know that this is a simple thing that would work, we'll use a cooling tower and the shell and tube to be our low temperature reference. This will work no matter what. It's a very simple thing. Now I've been showing that we're pumping the liquid up to a higher pressure with a cylinder and a series of check valves. What this program does is actually calculates the amount of mass flow rate that you're going to be using, and you need to meter pump that back up to the higher pressure instead of using just a fixed cylinder, which is going to require fixed conditions. So the reality is we're going to be meter pumping that back up into the system. Now the simulation program allows us to input how many BTUs we're going to bring out of the air. So basically this is the sizing. You would size it to kind of match your cooling tower, how much you take out, how much you put in, that sort of thing. So it allows us to adjust that so you can select the heat exchanger you want to use that your metering company pumps the liquid back in, and we call it the boiler. It's going to be boiling that liquid off. Now keep in mind this can happen at very low temperatures or high temperatures. That refrigerant or coolant is going to boil at whatever the temperature of the day is. That brings us back to the working cylinder through the solenoid valves. Then we go to the regulating or extracting of the energy and regulating the system. Now what we're doing on this is for this prototype, we're using it to use a pump hydraulic fluid, and the hydraulic fluid is going into a hydraulic motor, and what you see here in the picture is that we're using a fan as the load, but we really want to use a generator. So basically a prototype starting to look like something like this, but we could use this to push a generator to generate electricity to charge up your solar cells. You still want to have some batteries to level out the system so that you can have some place to put the power when you have more than you need and when you have peak periods where you use a lot of power, so the system doesn't have to be oversized. Basically, it's going to be putting out, if you make it too big, you're going to be putting out more power than you need for your peak times, and you're going to have to do something with that power. It's just conservation of energy.